Alright, welcome back. This is a summary of the first lecture of the analog design. We start our lecture by the question of what is a semiconductor. To answer that, we have a slab of material here. To calculate its resistivity, we have this formula. We have conductivity. In the macroscopic level, we can calculate it like this. For different material, we have different values. If we consider it which one is the conductor, which one is insulator, and which one is semiconductor, we have this graph here, and superconductors are here, but normally in the room temperature we cannot achieve to that. We should operate in the temperatures near the 0 degree Kelvin. So we have this formula for the macroscopic view, but what we want is the macroscopic view. We want to know how do atoms and electrons operate. For that, we need to get into some of the basic of the quantum mechanics. We have the Planck constants, and if you want to understand it better, I recommend you to watch these two videos. So we have this. We can ask, this equation means that if we throw something somewhere, it has a wavelength, but its wavelengths might be too small compared to its size. For example, if you even throw a ball to a wall, it has a wavelength, but its wavelength is so smaller than it's compared to its size, so we cannot sense it. If the electrons treated like a wave, what are the allowed trajectory? What does this wave represent? By the way, I show the question like this. I give you 1 second time to pause the video and think about it, and after that we will see the answer. Alright. These wavelengths shows the probability of presence of the electrons. So we have a wavelength that will show us the probability of the presence of the electrons. Alright. This allowed trajectory is sustainable. This is stable. So if this is stable, that means we have some unstable trajectories and places. To calculate that and get a sense of that, let's get into some mathematical calculation. So we have circumferences, which can be calculated from this equation. This is a relation between the radius and momentum, what keeps the electrons bound to the proton. This is the electrostatic attraction between the negative charge and the positive charge. So we have this electrostatic attraction and some centrifugal force, which is calculated like that, and some F and the circumference. So by these we can calculate, and we have also all the constants here. We can calculate it. So by doing some of the math and the calculation, we have the radius here, and we have n here, and we have the p here. This p is the momentum. Alright, so we have momentum here, and we have the radius here. Both of them have n, and n is the integer value, and it cannot be continuum. This is a quantized value. So what is the takeaway from this? As I just said, this is the quantized value. For the momentum and the radius, we have integer value of n. It is the quantization that happens here. So because of the wave particle duality, by the way, if you don't know anything of the definition, you can always highlight the text, click on the three dot and select on the smart lookup, and you can see the definition here. Alright, you have to be connected to the internet, but I'm not right now. So we have the momentum and the radius as a quantized value. Alright, now if it is is it always quantized? Well, no. What is it? What is its condition? We have to have a bounce state in order to condensation happens. In simple terms, it means that it has to have a total negative energy, kinetic and potential energy. If the total energy was positive, it means that it has a free particle. Okay, so we have to have a total negative energy. So we can show it like this: negative energy, negative, 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 and the positive energies are free electrons, which are shown like this. So the calculation can go like that, and at the end we get something like this. And if we have numbers here, we can get these numbers and the values. All right, these are called energy levels. So in order to have a bounce particle, we have to have total energy of negative. All right, and yeah, so this is for one atom. But if we have Z atom, they obviously, so let's see what will happen. We have two Z atom here and here, and we want to get them close to each other. If we put the nuclei right next to each other, what will happen next? According to Pauli exclusion principle, which is all quantum numbers cannot be identical when you have two electrons next to each other, we get a boundary of energy levels. It is called degeneracy of energy levels. At what distance, when does this Pauli exclusion principle kick in? Yeah, so let's ask this question in a better format. Actually, it's not the best format. We actually do not see it in the real world. One, because there are no two atoms with the same quantum numbers in the universe. If we are not in the 0 degree Kelvin, we cannot see this effect because of the noise. It is buried under these effects. The question should be how far they are apart before the degeneracy is noticeable, right? So since we are operating in solid state, we are dealing with crystal atoms, all right? And crystal atoms are stuff like that. As we are getting closer to atoms, as atoms are getting closer to each other, we get multiple energy levels with more degeneracy. So we have allowed band gap and a forbidden band gap here. We get so many electrons near to each other, and we have these band gaps of energy. By the way, we are looking at this for example like this, which is a space center cubic like this. We have all these 14 Bravais lattice in 3D. These are all possible lattice format. Right? We are just looking at this one, a basic simple cubic. In device physics, they will usually, in advanced device physics, we will consider this and study this. But for now, we just take a look at this one, and let's see what will happen if we plot the atomic spacing versus the diamond lattice spacing. Pay attention, diamond lattice spacing versus the atomic spacing. We have something like this. If you remember, we had 1s, 2s, 2p from chemical engineering, basic of chemical engineering. And for the example of carbon atom, which has 6 electrons, we get something like this: 2, 4. These layers will be full, and we can draw it like this. But from now on, we just draw the edge of these bands, valence bands and conduction bands, all right, to keep everything simple. So what is this? We have 3 layers here, but suddenly these two get merged and stuff like that will happen. It is actually called the hybridization, especially in sp3, which is here. It is sp3. So it has happened because of the carbon atom. It has 109.5 degree angles between it as a spacing that we get. So yeah, and because we're in the lattice, in the cubic crystal, and it has 109, some things happen because of this effect, and we get this. All right, more information I believe there are in chemical engineering that they will study about this stuff. So we have strong covalent bonds. This is carbon, 4 atoms. In a 2D structure, we can see them right there. And in a 3D format, we can see them right there. Covalent bonds, they are super strong. So at 0 degree Kelvin, is it a good insulator or a good inductor? Alright, as we just talked about it. It is an insulator because valence band is full, conduction band is empty, and the bonds are strong. So you have water analogy, which is something like that, which if we take a look at that, at 0 degree Kelvin, these two are full and nothing will happen if we move them. Alright, now let's talk about the band gap energies. Alright, let's take a look at different situations that what will happen. You have large band gap, you have electrons in EC conduction band, and we have overlapping band gaps like this, which every one of them will be considered as something. This one is insulator, this is metal conductor, and this is still a conductor. And we have another one, which is our desired one, which is with small band gap. So we have free electrons and holes. So if we want to take a look at how these electrons, how this electricity moves, we can say electrons are moving and holes are moving at the opposite direction of electrons. But wait a second, these electrons are obviously moving, but how holes moving? They are connected to each other with the hard covalent band. We can say one of the neighbors bonds will shift. It is a gradual transition. Alright, so this is a gradual transition, but these are hard covalent bonds. Then what's so less? Somewhat similar to what happens in the quantum tunneling, which you might already be familiar with it. Going from one energy state to another, which they are equal, they can cross from a small barrier. Similarly, breaking and making is a lot easier than just breaking, right? So electrons can obviously freely move, but these covalent bands are breaking and remaking. They are shifting, right? So aside from these, we have, if we are not in 0 degree Kelvin, we have thermally generated electrons, which are electrons that are generated because of the room temperature. And this gap can be calculated for different material. It is different. These are called device engineering, and EG can be calculated like that. So the bubble analogy can be shown like this. The bubble can be as holes, and the drop of water can be as electron. I haven't shown it here, and they can move like that. Right? So finally, this semiconductor that we are talking about, is it a conductor or insulator? We should ask at what temperature and at what band gap. It depends. We'll get to it in the next lecture. But for now, we have to remind that we have a combination and recombination and generation. We consider these as equal, right? In some cases where we don't study them here, but if we take the photons in the game, they will mess up with these two rates. Alright, thank you.